In this video series, I will introduce neuroscience research maps. My name is Alcino Silva. I'm a professor at UCLA Medical School. My laboratory works on molecular, cellular, and systems mechanisms of learning and memory. If you're interested to know more about our work and our laboratory, you can go to this website here, silvalab.org. This is me, actually, smiling in France recently. Research maps were introduced and described in a book that was published at Oxford Press in August of 2013. This book is a collaboration between myself, Anthony Landreth, a postdoc in the lab, and John Bickel, a renowned philosopher of science that did a sabbatical in our lab. Tony Landreth and myself recently have also written a paper published in Neuron in August of 2013 that summarizes research maps. I suggest you use the book and the paper as complements to this video series. Let's say that your research takes you to an area in which you need to find out something about neurofibroma and memory. You could go out and read 40 or 50 papers that describe what's known about the role of neurofibroma in learning and memory, or you could simply look at a research map that summarizes all of that information. For example, this is a cartoon of a research map. You can take a glance at this and have an immediate sense of what's in all of this information. So 50 papers may involve more than 1,000 experiments, and of course, this will take you many, many hours to get a sense of what's in this literature. And once you get a sense of what's in this literature by looking at the maps such as this one, then you can go back and look in detail at areas that you're particularly interested. The whole point of research maps is that there's just too much out there, and we need tools to help us navigate the immensity of the published record. So what's in a map? Well, one of the critical things in map are phenomena, things that you are interested about. For example, this is the transcription factor CREB, this is memory, this is PP1, a phosphatase. So you have phenomena. In addition to phenomena, you have connections between these phenomena. For example, this is an excitatory connection. What does that mean? It means that more of CREB should lead to more of memory, less of CREB should lead to less of memory. So an excitatory connection means that one thing excites the other. Of course, in addition to excitatory connections, you also have inhibitory connections, connections where more of one thing leads to less of the other. In these maps, you also have weights, and this is actually very, very important. Maps are not just cartoon summaries of what's known, they also give you a sense of the amount of information that's known about any one causal connection. For example, in this case, the weight is 0.5. Weights in these maps range from 0 to 1, and in this case is 0.25. What this tells you is that there's more information for this causal connection than this one here. So you have weights in these maps, and you also have experiment symbols. For example, this up arrow here tells you that one of the experiments that was done for testing and discovering this causal connection was a positive manipulation. This is an experiment where you increase the levels of CREB and then you look at memory. A negative manipulation, symbolized by this down arrow, is an experiment where you decrease the levels of CREB and you look at memory. A non-intervention is an experiment where you don't manipulate CREB at all. You simply look at the levels of CREB as they co-vary during memory. Does CREB activity goes up during memory formation, for example? That's what this experiment, a non-intervention, would ask. A mediation experiment is an experiment that you design to know something about the mechanism by which CREB affects memory. Of course, knowing something about the mechanism, about this connection, increases the reliability or the weight of this connection, so we represent this in the map too. So what will we cover in this video series? After this introduction on how to construct research maps, we will then cover components that are critical for research maps, including categories of experiments in neurosciences. Of course, you map experiments, you map experimental findings, so a basic understanding of the different categories of these experiments and how they are treated in the maps. It's critical if you're going to assemble your own map. Then we talk about rules that we use to assemble these maps. And I should mention that these are not rules that we invented. We simply articulated rules that neuroscientists in general use to interpret data and to evaluate the strength of evidence. So one of these rules we call the conversion tree analysis, another one consistency analysis, and mediation analysis. These are really the three rules that will go in depth. There are others that we'll cover, but we won't go in as much depth as these three different rules, which are really at the center stage of the maps that will show you how to derive. We'll then cover the approach that we developed to weighting causal connections. Of course, this is critical because maps are about phenomena and connections between phenomena, and we already covered that it's critical that we give weights to these connections because they give us a sense for how reliable those connections are, how much data is there behind these connections. So when you look at a map, you not only have a sense for what's in the literature in that area, but you also have a sense for how reliable, how much evidence is there for it. So these two components are really critical in these maps. In the final video of this series, we'll introduce a web-based application for deriving research maps. Although this app is useful in deriving these maps, it's not essential. I want to emphasize that you can derive your own maps with nothing else but the information in this video series and pen and paper. This brings me to the end of this first video, Introduction to Research Maps in Neuroscience. I hope that these maps will be as useful to your research as they already have been to ours. I dream of a future in which every experiment ever published is already in a map somewhere on the web, and every new experiment is immediately and automatically introduced into the map, so that all of us can go in and search this vast map and find the area that interests us. I think this will be an enormously powerful tool, and frankly, I cannot imagine a future of science without an application like this.